Okay, so I need you to buckle up. I need you to take a deep breath, breathe in, take all of that oxygen in, calm your nerves, because you're getting ready to talk about conformers of cyclohexane. And to be honest with you, this is a problem that a lot of people struggle with in organic. It seems like this is a thorn in people's sides whenever it happens. It's something that is very aggravating. It's something that deducts points off a test or off a standardized test, an entrance exam, because it seems like everybody wants to know about cyclohexane. And it's honestly not really that important. That's the problem with all of this. I mean, I know that conformers of cyclohexane is something that we should talk about and it's something that we should discuss, but quite honestly, I have worked in a laboratory environment for 20 plus years. And never once have I really stopped and said, I wonder what the conformer of that cyclohexane was that I used. No, give me a break. It's just something that they like to torture you with. That's all that it is. No one really cares about any of this crap, but it's something that we have to talk about. All the conformers, we have to talk about it. So I'm going to do my job. I'm going to bite my tongue, and I'm going to talk about the conformers of cyclohexane. All right, so here's the story with cyclohexane. I first just want to generally talk about rings. Notice that we talked about torsional strain. The last video that we talked about the rotations about the bonds and so forth, and this is why the bonds typically position the way that they do. And we talked about the anti, and we talked about staggered, and we talked about eclipsed. Okay, well, folks, that's why we do the jiggy-jaggedy thing in organic, because this whole zigzag kind of zipper looking notation is making sure that everything is in a staggered position. That's why we do that. All right, staggered is the most stable. So even in our skeletal structures, we are actually representing staggered notation, whether you realize it or not. But that's why we do that. And that's why we just don't draw these things in a straight line all the way across. So the zigzag allows us to denote that staggered positions are really included in our depiction. Okay, so that's just a side note. But this happened because of strain. We wanted to prevent strain from happening. We didn't want the molecule to be in a position or contort itself in a way that it was uncomfortable, right? I mean, it's yoga. It doesn't like yoga. It doesn't like to be in those weird kind of bendy shapes that makes it very uncomfortable. So it takes the path of least resistance. And the path of least resistance is the staggered conformer. That's what it likes. Well, rings are no different. Cyclo groups have conformers. But they're a little strange because they're a ring. It's not a straight chain. So we have to kind of look at a ring system first and then talk about some ordering that goes on the ring system. So all cyclos have what we call ring strain. And this really gives rise to the whole idea of conformer yet again. Right? Straight chain molecules, we talked about torsional strain. Here we're talking about ring strain. Oh, so carbon is normally tetrahedral. This is a carbon-based course, right? And tetrahedra is 109.5 degrees. Okay, that's the bond angle that these carbons really enjoy. We make them happy, right? They do a lot of things for us. They help us breathe. They help us see. They help us walk. They help us talk. They help our headaches go away when we take that aspirin pill or that medication. And we want those carbons happy because they do a lot for us. They do a lot of work. So 109.5 is the preferred bend that they like to be in. All right. Well, the problem here is that we have a ring, and that ring could be a 3-carbon system. And that is what we would call cyclopropane, right? Well, if we take a look at the bond angles here in cyclopropane, this is actually a 60-degree angle. That carbon does not like the 60-degree angle there. It wants 109.5. So cyclopropane has quite a bit of ring strain. That means if given an opportunity, pop, this ring will go pop, 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 pop. That kind of sounds like It, if you ever saw that movie, didn't it? All right. So cyclopropane will pop open. And when it pops open, it's no longer a ring. So that ring is very unstable. And it's for that reason, ring strain. It's all about the carbon angle. All right, well, we can have 4 carbons in a ring. And this would be called cyclobutane. These also have bond angles. And guess what those bond angles are? If you guess 90, you're correct. So there's still ring strain on cyclobutane as well. All right, we're getting closer. We're getting closer to that 109.5. But this ring is not ideal. This ring stays around a little bit longer than cyclopropane does. But if given an opportunity, this ring will pop open and we don't have a ring anymore. So that ring is slightly unstable. All right, then we go to a 5-membered ring. There we go. 5-membered rings. Not the best drawing, but whatever. I'm not an artist. And then we measure this angle of these carbons. And what you'll see with the 5-carbon ring is that this will have a bond angle of 108. All right, so 108. That's super, super close to 109.5. So cyclopentane is actually the best ring so far. And cyclopentane does not have a tendency to pop open. And the reason is because carbon knows it's uncomfortable, but it's only by 1 degree, whatever. That's not a big deal for it. So it's going to hold the bond angles. It's going to hold the ring structure. That ring is going to stay around for a very long period of time. And it is a pretty stable, well-formed ring for me to do things with in a laboratory environment. And that's why it stays around. Because all of those carbons have a closer bond angle to 109.5, especially compared to cyclopropane and cyclobutane. Then we go one more up, and that's our 6-carbon ring. All right, so 1, 2, 3, 4, 5, and then 6. There we go. All right. Now, I'm going to be honest with you. Some instructors do not like this because they see this as oxygens, and they, you know, you do this, you should be coloring them in. All right. I know that's kind of confusing, but this is a way that I keep the number of carbons straight. I mean, I do this because I want to make sure that I am including the number of carbons that I need to be drawing into that structure. And that's one of the ways that it keeps me on track. True blue skeletal structures, though, I mean, it should just be this and that's all. Or it should be this and that's it. So if you are doing what I do, just go through and darken in those circles. So if you have someone else for an organic course or a science course later on down the road, they're not going to think that you have just drawn a ring structure that is full of oxygens and not carbons, because that's the exact thing that they're going to say. All right, so back to the point. Cyclohexane. All right, so cyclohexane, again, I'm going to measure the bond angles here. And if we measure the bond angles of cyclohexane, what you will find is that those are almost perfect. So cyclohexane is going to be the best ring choice that's out there. It's also the most stable ring choice that's out there, because these angles are very, very close to 109.5 for those carbons. All right, it just has a little bit of extra wiggle room compared to the cyclopentane, but because of that, it gets even closer to the ideal bond angle, and that is what this is all about. All right, so cyclopropane, cyclobutane, cyclopentane, cyclohexane, and folks, we can go larger. We can go cycloheptane, cyclooctane, cyclononane, cyclodecane. We can do that. But after carbon number 6, when we go 7, 8, 9, 10, and more, then the ring becomes very floppy. Floppy, otherwise loose. And we don't like loose rings. Those rings are not very stable either. So cyclohexane is what I would call the Goldilocks of the rings. It is just right. Anything below 6, there is some problem associated with it. And anything above 6, there is some problem associated with it. And 6 carbons in a ring is almost magical. I mean, they get along so great. The carbons have ideal bond angles. Everything is ideal in a magical utopia for those carbons and hydrogens. 7, 8, 9, 10, too big. Too big of a ring, too floppy of a ring. They don't really stay around and stick together like they should. Anything lower, 3, 4, 5, those bond angles are a little bit tighter, and the lower that you go, the tighter that they're going to get, and the more unstable that they become because they want to pop open. They do not want to keep that ring formation whenever they can. Okay, so now that we've got that out of the way, what I want to do now is show you a vision of cyclopropane. And here you go. Cyclopropane, not the best ring. But the reason that I'm doing this is because I want you to see from the side view of cyclopropane. And this is from the side view of it. Not looking down top like you would draw it out on a sheet of paper. Looking from the side. When I look from the side, it's very clear that this ring has a side. And in the way that this is depicted, a top side and a bottom side. It looks like I have a side that has these hydrogens on the top, and then on the other side of the ring, I have a side where these hydrogens are down below. Right? I mean, that's kind of clear when I begin to look at it this way. Well, here's cyclobutane. Notice the ring gets a little kinkier. It's not as flat. There's a little kink in one of the carbons. That's because there's an extra carbon there. The bond angle gets a little bit bigger. It's not as flat. It's okay. But again, notice from the side, I can visually look at this and tell that there is a top side to this thing, right? That includes that one. And then there is a bottom side to this ring that includes those hydrogens. Again, we're talking about sides. A top side and a bottom side. A top half and a bottom half. All right, so here's pentane. Pentane, they like to kind of make you think of an envelope that's kind of opened up at the lip. That's really the structure of how this thing looks. But once again, we're kind of looking from the side, not as well as some of the others. But as you can tell, there is going to be a distinct top side and there's going to be a distinct bottom side to that ring. So the bottom side and the top side of the rings are going to be very important. I keep mentioning it so far, right? And cyclohexane, that is the best ring of them all, will also have a side view. And this is how we represent the side view. On a sheet of paper, the best way that I can draw these, you might come up with a better way, but the best way that I can draw these is to start off kind of like this, 2 lines parallel, and one end gets kinked up and the other end gets kinked down. Think of this as that envelope with the lip, but then there's also a lip that points down as well. And here's my 6 carbons. All right, there's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. There's my 6 carbons in total. So this is the side view of cyclohexane that we will start looking at. We're also going to have to get comfortable drawing these, and that's because a lot of these questions will include this particular type of drawing of cyclohexane. The top view of cyclohexane would look like this. 6-membered ring, 6 carbons all the way around. This would be the side view of that ring. We know that it's not a flat ring. We know that one end of the ring, bink, points up, and one end of the ring, boink, points down. All right, so there is the representation of cyclohexane that I'm going to have to start getting used to. If you have one of these that point up, and if you have one of these that points down, we're going to call this a chair conformer. Oh, and I see where this is going now, because conformers were talking about different positions, right? So when we talked about the straight chains around rotations of a carbon bond, it was all about the positions of those groups that were on there. Were they staggered? Were they eclipsed? Now I see how the term conformer is coming into the picture. Conformer is looking at the structure and saying, listen, here is the ideal situation for cyclohexane. And from the side view, if one points up and one points down, this is going to be called the chair. All right, well, there's another option that this thing can do. The other option is that I can have these two things, and one lip points up, and on the other side, another lip points up as well. So there's my 6-membered rings. So this lip actually just gets pulled up. And this is something that we call the boat conformer. And as you can tell, it kind of looks like a boat, doesn't it? The tips of the boat are on each end. Well, out of the two choices, the chair conformer is going to be the most stable. But just like with single bonds, we said that they rotate 1 million times for every second. And it kind of happens here with cyclohexane as well. This bond will flip up, or this piece will flip up to make a boat. And then this piece, or maybe this piece, could flip down. And if it does that, it makes a chair. And those lips will keep flipping back and forth, back and forth, back and forth, back and forth. And this conformer goes from chair, boat, chair, boat, chair, boat, chair, boat, just like staggered and eclipse does in a regular bond with a straight chain molecule. It flips as fast, but it does have a preferred method that it wants. And that preferred structure is the chair conformer. That is what it really prefers. So when it gets into this position, it's going to stay in this position a little bit longer. Then it does flip to boat, but whoop, back it goes back to chair. So the flipping still happens, the movement still happens, the change in conformer still happens, just like with staggered and eclipse. There is no difference. But this is the relationship between the chair and the boat. Now, some people like to talk about what they call a half chair. Give me a break. Those people just want to make your life complicated. What that means is that this piece of the chair will start to get pulled up, and this becomes very straight. It's halfway to the boat is what that is. So chair goes to half chair, then goes to boat, or what they would call twist boat. Okay, all of that stuff is just craziness. I don't even want you to think about it. But if you read your text, they're going to mention those as possibilities. And then they don't do anything with those possibilities after they mention it. So whatever. That's why I'm telling you to forget about it, move on about your business, and only worry with chairs and boats. All right, so in the chair conformer, I'm going to redraw this again. I get a little lazy and sloppy on them sometimes, so please forgive me. There's going to be carbons on each one of these. I'm going to draw those as circles so that way you can see these a little bit better. We have proper names that are related to the types of bonds that are on these carbons, because what we're going to see, this is 3D, right? This is actually taking up space. And what we're going to see on the chair conformer is that sometimes, let me change my color. These bonds that we want to refer to go straight up and straight down. Straight up, straight down. Straight up and straight down. All right? So each one of those carbons, they have a bond that either goes up or down. Up or down. And notice the way that I did that, they alternate. If I do this one straight up, the next one is going to go straight down, then the next one's going to go straight up, the next one goes straight down, the next one goes straight up, the next one goes straight down. So sometimes we want to focus on those particular types of bonds for various reasons. You'll find that out much later in the class. And if we're referring to those bonds that go straight up and straight down, those have a proper term that we call axial. So those are axial bonds. So the chair conformer of cyclohexane has axial bonds that alternate up and down. All right, so there's some terminology for us to get started. Then the chair conformer, because each one of these carbons has to have 4 bonds, right? Here's 1 to the carbon. There's 2 to the other carbon. Now we talked about a third that either goes straight up or straight down. That's an axial bond. So they also have to have another bond here. And this also goes up and down, but it's not straight up and straight down. These are more off to the side. All right, so here's how these are operating. Notice this axial bond, I just pointed up. Okay, straight up. Well, that carbon has to have a 4th bond. And these are not going to go straight up or straight down. What they're going to do is slightly go out, up, and out, down. So slightly out and down, slightly out and up. Slightly out and down, slightly out and up. Slightly out and down, slightly out and up. So the axial bonds are full-fledged, fully up and fully down, like flagpoles. And these bonds are not quite that way. They more get pointed out. Think of it as kind of like wings on an airplane. And those wings go slightly up or slightly down depending on which carbon they're attached to. But the same thing kind of happens here. So they still go up and down, but I'm going to put just slightly. But we still see that orientation on them. And they still alternate, don't they? Notice what I did. Down, up, down, up, down, up. And these are going to be called equatorial. So cyclohexane has a chair conformer. And in the chair conformer, they have 2 different types of bonds on each carbon. One is an axial bond that points straight up, straight down. And one is an equatorial bond that points out and slightly up, or out and slightly down. Now I'm going to put those 2 diagrams together because that's how they are in real life. All right, so I'm going to draw my cyclohexane. There we go. I'll draw my dots in here for all my carbons so you know what they are. And my axial bonds, up, down, up, down, up, down. And then I have equatorial bonds. Now I've got to be really careful when I put these on here. The starting one is always the best one. That's always the one I want to focus on. So up here is normally where I start, this kind of peak. And this axial bond goes straight up. So this equatorial bond is going to go slightly down and out because of that reason. This goes straight down, so this will go slightly out and up, slightly out and down, slightly out and up, slightly out and down, slightly out and up. And there is cyclohexane with the representation of the equatorial and axial bonds on each carbon. And the reason that this is important, because I have kept stressing the up and the down part. And that's going to be very important. So later on in this lecture series, a couple of videos, I know, more and more and more, oh God, when's it going to stop? We are going to refer back to this up and down notation. And it's very important that I draw them and set the template the right way. Because if I can't set this template the proper way, then I won't be able to answer those questions the proper way either. So equatorial are like airplane wings that go slightly up and slightly down. And the axial bonds are like flagpoles that point straight up or point straight down. Here's a better representation maybe of an axial bond and a cyclohexane drawn in a different way. It's still from the side view, a little bit different than mine, but you can kind of still see the kink that's in there in the chair conformation. So those are axial bonds. And then here is representation of the equatorial bonds. Slightly down, slightly up, slightly down, and slightly up. And then here is a better representation of both of those together on a cyclohexane ring. Now, I'm going to be honest with you. In a normal organic class, they probably would plaster this up on the board and that would be it. And they would say, here's the side view of cyclohexane with the axial and equatorial bonds. And then they move on. That's all that they do. And then it's up to me to go figure out what that really means. Or it's up to me to figure out why this is so important. And they never really took the time, for me in organic, to really fully hash out what these axial and equatorial bonds are before they started to go into these example problems. But that's what I'm going to do with you. So I know it's another video, but at the same time, it's another video that talks about the basics. It talks about the foundation of what these axial and equatorial bonds really are and why they are so important. You know, why do we go through this mess in the very beginning? And that's what we're going to do in the next video. So in the next one, we might take a look at a few example problems, but I'm going to hash out more about this theory of axial and equatorial bonds on a cyclohexane ring first.